So we've already looked a little bit at what cathode ray tubes were and how they helped J J Thomson come to a better understanding of what the nature of the atom was. J J Thomson's model of the atom was this plum pudding model or this chocolate chip cookie model, where these electrons are separate from this positive charge. So this was the first time that scientists really understood that positive and negative charges were separate in the atom. And J J Thomson orientated them this way, where these electrons are these negative bits clumped into this positive framework. What we're going to look at is we're going to look at the experiments that J J Thomson did and their significance in determining kind of a little bit more about what the nature of the electron and what the nature of the atom is. So J J Thomson took these cathode ray tubes. If you look at these cathode ray tubes, these electrons are first accelerated through this set of parallel plates, and then they reach this region where we have magnetic fields and parallel fields that can be manipulated. And the first thing J J Thomson did is he exposed these electrons to only a magnetic field. So if we think about what's going on here, we want to ignore these parallel plates right now. And we're going to look at only this magnetic field. So using our third hand rule, we're going to use our left hand because electrons are negatively charged. We need to think of these fingers as going into the page because that's the direction of the magnetic field. Then the magnetic force experienced by those electrons is going to be in this direction. It's going to be down. So these electrons, as they travel through this region, are going to be pushed down and maybe end up somewhere over here at the end of our cathode ray tube. Now we can do another experiment where now we turn off this magnetic field. So now we're going to ignore this magnetic field. And we turn on these parallel plates. So I have a negative plate here and a positive plate here. Because those electrons are negative, they're going to be pushed away from that negative plate. And the electric force will be in that direction. So if we only turn on those parallel plates, the electrons are going to travel through and be pushed somewhere around here. Now it gets interesting when we actually turn both on, and we can manipulate those two forces, manipulating the fields to a certain point where this electric force is equal but opposite to this magnetic force. What happens then is that only electrons traveling through at a certain velocity will actually travel straight across. Because those forces are equal but opposite, those electrons aren't deflected one way or the other. And now because we have forces that are equal but opposite, we can actually come up with an equation that allows us to determine the speed of those electrons. The electric force is my electric field times the charge, and this is QVB. So I can rearrange that equation and actually get the speed of those electrons can be calculated at any time. It's my electric field divided by my magnetic field. We call that the velocity selector formula because it allows us to actually determine the speed of electrons traveling through these cathode ray tubes using electric and magnetic fields. Now, this is an important step in determining the charge to mass ratio of the electrons. And if we skip ahead to the next slide here, we have a question where we're recreating Thomson's experiment. We set up our cathode ray tube with an electric field and a magnetic field. And when we do that, those electrons travel through undeflected. So I have my electric field equal but opposite to my magnetic field. Then what happens next is we turn off that electric field. And what we find is that those electrons start to travel in a circular path. So there's only a magnetic field, a magnetic force experienced by those electrons, and they travel in a circular path. So because it's traveling in a circle, Well, this magnetic force is actually the center seeking force, the centripetal force. Using this relationship, we can determine the charge to mass ratio of the electron. But first we need to think back to this first part of the experiment. This first part, if you think back, allows us to determine the speed of these electrons. It's my electric field divided by my magnetic field. And that's the speed that those electrons are traveling at. We're going to need that later when we jump ahead now to the second part, where I know now that my magnetic force, QVB, is equal to my centripetal force, mv squared over r. Now the charge to mass ratio is the relationship between charge, which you'll remember is Q, and mass, which is m in our equation. So we can rearrange this equation to get the charge to mass ratio. Q over m is equal to V, my speed, over my magnetic field times the radius of that circle. Now this is where we go back to the first part now, and where the speed of those electrons is important. Because I can use this relationship to determine the speed of my electrons. So this equation now becomes this: Q over m is equal to my electric field over my magnetic field squared times the radius of that circle. So I can calculate the charge to mass ratio. Looking back up top, I have an electric field of 1.86 times 10 to the 4 newtons per coulomb. I have a magnetic field of 5.80 times 10 to the negative 4 torr, and that's squared. And then I have a radius of 0.325 meters. So I put all those values into my equation, and I calculate a charge to mass ratio of 1.70 times 10 to the 11 coulombs per kilogram. And this is actually pretty close to what our present understanding of the charge to mass ratio is, which is 1.76 times 10 to the 11 coulombs per kilogram. Now, this was an important experiment, and it was the first time that scientists had an actual look at what actually composed the atom. This number is really big. So we know that there's a lot of charge on a very small particle. So it was their first real glimpse at the actual nature of the atom and what electrons actually were.